Oh, hi. So welcome everybody to my presentation here on ultra-low latency with Java and terabytes of data. My name is Per. I was born in Sweden on the west coast and moved to the US on the west coast. And a lot of water had passed under these bridges since I started with Java, back in Java 1.0. I've been the co-author of Modern Java, a publication with DZone, and I've talked in many events, including Java 1. And this is the third time I'm here in memory computing. Okay, so I'm going to talk about this. Isn't it annoying? Latencies, we all hate that. So, of course, low latency is the opposite of this. So we want to remove this. How many of you guys have seen this? Of course, everybody has. How many of you are programmers and have included this in any of your applications? I'm guilty. Okay, so we don't want to do that. We want to have ultra-low latency. And when I talk about ultra-low latency, I mean 200 nanoseconds. Maybe that's just a figure for you, but it's quite a short amount of time. I will come back to exactly how short it is. But it's a very low latency. So how, but what are the problems? Why are things slow? These are some of the examples of why your application can be slow. You can have slow database. You might have data on several nodes, and the data is not correlated or it doesn't have affinity. Data is generally remote in some sense, or you can create a lot of objects in your Java virtual machine, or you just have lack of parallelism, you can't use all the CPUs that you have. These are just some samples of things that can slow down your application. And let's start with slow databases. This is common knowledge, so I will not talk so much about that. Everybody knows that the more data we stuff into the databases, the slower they get. I'm going to focus on another thing, which is not so well understood in the community. If you have low affinity, and what do I mean with low affinity? Affinity is when things are related, more or less. So if I have something here that's related to something else, I know that they will fit together and are referenced in the same context. I will come back to what that is. So you can, if your data has low affinity, you can't scale out and have low latency at the same time. It's impossible. You can have low affinity and scale out, but then you don't get low latency. Or you can have low latency and when you have low affinity data, but then you can't scale out. So this is a hassle. And why is it so? Let me explain that. So let's see. We have the blue squares and the blue triangles. They kind of are together. And we have the red squares and the red triangles. They're also together. So maybe the squares are pants and maybe the triangles are shirts. And the blue ones are for men and the red ones are for women. Then you understand better what this is. So I can take all the men's wear here, compute something. I use this one, and I can take all the women's stuff, compute something, and then combine the results, and everything is good. In this case, I have affinity. I know that men are at least unlikely to wear female skirts and vice versa in this example. So I have affinity, and therefore I can get low latency, and I can have scale out. But if I don't have affinity, say there is a new trend with a unisex shirt. So they are indicated by white here. So you don't know whether it's a man or a woman who is going to wear these shirts. So how do I scale out? Well, one option would be to place all of the shirts on this node and all of the same shirts on this node. And then it will still be fast, but then I don't have any scalability. Because this triangle here might represent one skirt, but it might also represent 1,000 thirds or 1 million or 1 trillion shirts. So this is not scalable. So, but another strategy can be that I place some shirts here and some shirts there and hope for the best. But that will, of course, fail because sometimes the shirts are needed by node number 1 and node number 2. They have to send data back and forth here. And there goes my latency out of the window. So, and that's just a simple example. What if I have 8 different object types here and 8 nodes? What will happen then? Or if I had like 256 different objects and 2,000 nodes, then we might end up in something like this. And we don't want to do that. So we can't get scale out, low latency, and low affinity at the same time. Let's talk about something else. Let's talk about the laws of nature. They can sometimes be very irritating. Let's suppose I have my computer here in San Francisco, where we have our office, and I want to retrieve something from New York. And the shortest time I can do that, according to the laws of nature, is 45 milliseconds if my signal goes into fiber, because that's the speed of light. I'm limited by the speed of light. And this is vastly more than 200 nanoseconds. So that is completely out of the question. This is not a viable solution. So let's go in the other direction. What if I just take two servers and have a switch and just connect them via the switch? That must be much faster. Yes, it is. But that's 100 microseconds. That's still 500 times too slow. 500 times. So what if I remove this switch here? Then it can be faster. If I just connect one server to another server by a direct cable, and I tweak the kernel, I do busy polling, and I do affinity pinching of my process that receives the data via the TCP/IP stack, then I can, by using those black belt techniques, come down to maybe 25 microseconds. That's more than 100 times too slow. So this leads to the conclusion that if you want ultra-low latency, what I mean by ultra-low latency, exclude having your data on different machines. Okay, but what if we have them in different processes? What if I have like an EH cache or some other things having all my data, and then I just invoke a system call and retrieve data? That's much faster. Yes, it is. If you do a system call, it's maybe about 2 microseconds. So that's maybe 10 times as slow as I would need. And that's just only for the context switch. And if I do a context switch, I will ruin my cache, CPU cache, and everything. So my program will run slower after a context switch anyhow. So I don't want to do that. Even that is too far away. So, and another thing is object creation. And this is probably the least things on a page you have ever seen in this summit. 1 second. What is 1 second? Yeah, that's a typical garbage collect. Garbage collect in 1 second, half a second, 10 seconds, a minute, or even half an hour if you're unlucky. The problem is when you create objects, when you create objects, they need to be collected. And under some circumstances, with a high pressure, the JVM needs to stop all the threads and clean up stuff that they couldn't clean up because they were permutating the JVM, so it couldn't clean it while the program was running. And 1 second is like 1,000,000 times too slow. So that is not good. In fact, just writing a single Java object to main memory takes 200 nanoseconds. Just writing. This is the shortest Java object you can ever do. If you just extend object and write that to memory, it's 16 bytes, 128 bits. So the conclusion is you can't create shared objects. Then it's not ultra-low latency anymore. So that gives you an idea how short time 200 nanoseconds is. It's a tough challenge. Okay, another problem is lack of parallelism. This is an annoying thing. You have 32 threads. You run something, and your Java app is stuck at 100%. Can't be parallelized. I've seen this many times. Have you seen it? Yeah, some of you? Yeah. Very annoying, especially if it's locked like that. A thread that's spinning and just consuming CPU time. So that's another problem. So the solution here is to do something called In-JVM memory. And what is In-JVM memory compared to just in-memory? In-memory, it's a well-known concept. You have your data in RAM, and the application is remotely connected to your data, but in a grid or in another machine or another process. Well known, so you have the memory here and you have the application here. In-JVM memory is something more. Data is still in the RAM, but the application and the data resides in the same JVM. That's a very important distinction in terms of ultra-low latency. So this is a picture of a modern CPU. It's an Intel CPU with 8 cores, as you can see here, 1, 2, 3, 4, 5, 6, 7, 8. And this middle part here is the L3 cache, which is a shared cache between the CPUs. And here they have the L2 and L1 caches. So you want to run your code there. If you can hit the L1, you get 0.5 nanoseconds. L2 is 7 nanoseconds, and L3 is 20 nanoseconds, approximately. Depends on what CPU you have. So these figures are completely different with the other figures I've shown you before. They are orders of magnitude faster. So this is where we want to be. And if we miss the cache, we have to go to main memory, and that's 100 nanoseconds. And that's half our budget. So we can only do 2 memory references of 64 bits if we want to do ultra-low latency. But this gives an opportunity to really do it. So this is an example of an illustration of performance with in-JVM memory versus regular in-memory performance. In this case, it's 100 times faster, but usually it can be even more. So that leads to the next question. That sounds good, but how can you do this practically? How can you have such big machines, and how can you really work with them in a doable way? Well, let's look at this picture first. Last year, mankind passed an epic point where 1 gigabyte of memory cost less than a coffee on Starbucks. So memory is cheap. And you can scale up, because you need to scale up. Today you can scale up to 12 terabytes. If you have 4 of those guys here, you can get 12 terabytes. You can go online to AWS and buy 12 terabytes if you want. And I have reason to believe that we soon can scale up to 48 terabytes in a single machine. Quite soon. Another thing is that you don't have to buy 12 terabytes from the start. You can start off with a small container, and then you can play around with the CPU, the amount of memory and storage, for example, on AWS or Google Cloud or whatever provider you're using. So you can grow as your data grow. That wasn't the case when scale-out first came, because then you couldn't. Then you usually had physical machines, and that was a big advantage. You can just add nodes. But now it's much easier to scale up than it was before. Okay, but that sounds good. But wouldn't that cost you a fortune? Don't you have to give an arm or a leg for that big machine? This is what I thought, and I talked to some of my guys and my colleagues, and they thought the same. If you buy small machines, they're relatively cheap, but if you want to buy bigger machine, they're much more expensive. But I was wrong, and they were wrong too. If you check the facts, and for example in AWS, you check the machine called X1E, something X large, and you plot the size of memory against the cost. You see it's not even approximately linear, it is exactly linear cost. So you pay what you get. So that is good. Okay, but what if I have more than 12 terabytes? I mean, most people don't, but some people have more than 12 terabytes. Then maybe you can apply some kind of high-level sharding. Maybe I can work per year with a problem, or per region, or per segment. So I can divide my data into bigger chunks. And then take the nuisance of maybe querying 3 different nodes and do a manual aggregation of what's in the different shards. Or maybe you can use memory mapping. I don't know if you saw the talk about by Intel a few hours ago. They talked about IMDT, which is a way of using an SSD to map RAM. So it looks like RAM, but it's actually SSD, a very rapid SSD behind. This will of course make it a bit slower, but still very fast. So then you can have bigger machines. And maybe you don't, if you have 12 terabytes or more than 12 terabytes, you might not need to use all the terabytes to solve the problem at hand. You might only need a subset of what you have. Okay, but if my data grows, maybe I'm here 2008, and 5 years later I'm here, and I will see that I will not be able to fit my data in, because at that time I only had 400 megs. But as time passes, my data grows, but the good thing is that also technology-wise, the maximum node size will grow. So in this example, we have a doubling each second year of the maximum RAM size. This is another way of seeing it. If we have data that has a certain affinity or a certain correlation, working with them on a single node will have a good performance all the way up to the limit of what you can have, and then you will not have any performance at all. Whereas if you scale out, your performance will very rapidly drop. As soon as you go from 1 to 2 nodes, it will drop immediately, and then you will be pretty much stable, but very low performance. So there is a price you're paying for scaling out. But there are some cases, and many cases I would say that scale out is good. But this is really the sweet spot of In-JVM memory here. You will always have a lot of better latency than if you scale out. Okay, so you remember this. We can't have low affinity, low latency, and scale out at the same time. But if we can scale up, we can have In-JVM memory technology. Okay, that was about In-JVM memory in general. Now I'm going to talk about our company and our product, which you might have guessed is based on In-JVM memory technology. So how does it work? Well, it continuously creates data snapshots from a data source. The data source can be, of course, a database, but it can also be a flow of information like Kafka Stream or something else. And it places a copy within the JVM. Everything is off-heap. So all the data that's being pulled in is stored off-heap. All the indexing is also off-heap and has no impact on garbage collection. So whether you have 10 gigabytes or 2 terabytes, you will still have the same garbage collect time because the garbage collector will not even see the data. It's outside the Java heap. It supports off-heap joins and aggregation, so it can operate without creating intermediary objects. This is a very important property. So you can traverse your data, you can create joins and aggregation without creating any Java objects. So the aggregation will be performed off-heap too. Okay, that sounds cool, but how do you use it? We have opted to use the standard Java util stream interface. So everything in Speedment is a stream. Now, this is an interface in Java, so you can make your own implementation of a stream. But the way you're using the stream is standardized. So you can find a lot of programmers who know how stream works. And I wrote an article in the Oracle Java magazine about a year ago about this. In this case, it was like converting Java streams to SQL, whereas when we do it in memory, converting it to an in-memory traversal graph. So this is an example of the similarity between SQL and stream. They are both called declarative constructs. And that means that we are saying what we want, not how we want it. So if you see this first line here, select star from film where rating equals PG13, it says that from the database, I want each and every film that satisfies this requirement. It doesn't say how the database should do it. The database is free to iterate over each and every film, which it probably will not do, and evaluate the filter, or you can use an index. And probably it will use an index. The same is true with streams. It doesn't look that way. It looks like we are creating a stream over all the films, and then we are applying the filter. But that's not the case, because this first stream, when we apply this filter, creates a second stream that can utilize internal indexes. And that is cool. So what a stream is really a functional composition of things. So we compose a function by applying a lot of operation in the stream pipeline here. So this is one example. I take a film, create a stream, I filter out all the rating that equals PG13, and then I count the occurrences of all those films. So Speedment is able to unwrap this functional composition and flatten it out. So it can do all this without creating any objects at all. It sees that, it has something to do with films, and I am only interested in these films, and then I want to count them. So I don't need to create objects just for the sake of counting them. I can use the index here and just count how many are in that bucket, so to speak. So this will only produce a long as a result, no object whatsoever. If I do like this, more advanced, instead of counting them, I collect them using a collector here, and this is a JSON collector that extracts length and title from a film. And this is a Speedman collector. The collector is a standard interface, but this is a particular implementation of a collector. So it will be able to recursively go down and see what this does and perform this JSON conversion totally off-heap without deserializing any films. It knows where length and title are placed off-heap, and it can extract just those elements directly. And it can build up and do a mutual reduction on this collector here. So that's cool. Same thing goes with joins. So here we have a join that we basically, if you look here, we have an inner join where we join a language table with a film table, and we join on language ID. So this is basically, you have a film and we have a language, so we join them together. And this is the definition of the join. Then I have a definition of an aggregation, which is basically, I have a builder that allows me to build aggregations, and I want to have the language ID as a key. This is basically a grouping by operation. I will have another key on the rating, and then we'll compute the average of the length. This is what this aggregation does. So when I have those two, I can combine them. I can have this join, create a stream, and collect them with this aggregation. And the cool thing is that even with this more general aggregation, everything takes place off a heap. So it's able to unwind everything, all the filters, sorting, whatever you have in your operation, and then apply this aggregation, and everything is off-heap. Well, if I want parallel, how do I do that? That's so simple. You just add the keyword parallel, and now this will be performed in parallel using all the threads on the fork join pole. So they will, each and every thread will take their share, collect them to their own off-heap aggregation, and then those off-heap aggregation will be combined, yielding their end result. So that solves the problem. So now you have all your 32 threads, you can use them here. So that was that part. That was the theory. Now we come to a demo. How does it work, and how is the latency? Before I start with the actual demo, I'm going to show you what code I'm going to benchmark here. This is very similar to what you said before. I have a benchmark using a JMH micro harness for benchmarking JVM applications here, and I compute the count of films where rating equals to PD13. So this is what I'm going to do, and this is going to be done millions and millions of times, and then we're going to compute the average latency of that. And that's going to be made in two cases. The first case, we're going to connect to a database. So this stream is going to be converted to like select count star from film where rating equals 13, and send that to my database on my local machine. And in the second case, we're going to pull in the entire database into JVM memory, and we're going to run it from there. And that's what we're going to compare. And this database I'm working with is an open source database called Sakila, which models kind of a DVD rental store with films and artists and stores and costs and customers and a lot of other things. You can download that for free. It's open source. So what I've done was that I go to our homepage, to the initializer. I check in here. It's MySQL. I use Java 8. I would like to use in-memory acceleration, and then I click download. This will create my POM file, so I can just launch it from there. So there's a plugin for Speedman. When I launch it, I get this dialog. So I have a MySQL. I write the credentials and hit connect. So then Speedman will retrieve all the metadata from the Sakila database, and, and present that in a user interface here. So here you can see all the, for example, all the tables: actor, address, category, city, country, customer, and film. Film is what we're interested in right now. And here we have all the columns, foreign keys and indexes and whatever. You can also change a lot of things here if you want to create a custom code. In this example, I didn't. I just pressed generate here. And so the complete Java domain model was generated automatically from the database. And from that, I'm going to switch to my IDE. Can you see this? Okay, good. So this is, you will recognize this part. This is what I show. So this is the benchmark I'm running. And I'm running two variants. I have this parameter here, which is if I'm going to use JVM, In-JVM acceleration or not. So first it's false and then it's true. So it will run two different tests. So now I'm going to start that. And it will take about a minute. So now it starts, and it conducts two runs. First it runs as a warm-up to warm up the JVM, and then it runs the actual test. So the first test is running against the database. And that will soon be completed. Hopefully, I would say, because it's a demo, you never know what happens. There, okay. And now the second is going, and then you can see here we pulled in 50,000 entities from the database into the in-memory store, and that took 1.5 seconds to pull it in and to create all the in-memory indices. And now the warm-up is completed. And in about 15 seconds, we will see the result. What a cliffhanger. There we are. Okay, so we can see that if we didn't use In-JVM memory and connected directly to the database, which was on the same machine, we have an average latency of about 1 millisecond. But if we use the in-memory store, we have a latency of 10 to the minus 7, which is 100 nanoseconds, which is half the time I promised you. So let's see how that looks more graphically. So if I put in the latency for MySQL, it was 0.001. Yes. And the other one was 1 to the minus 7. So of course, you can have also make the column here. The latency was 100 nanoseconds, and this is 1 million nanoseconds. So you can't even see a pixel here. That's the difference. It's so much faster. It's a tremendous difference in terms of latency. And of course, latency is related to capacity. If you only have one thread, you can invert latency and you get the capacity for that thread. So this will allow us to do 10 million operations per second per thread on a laptop. So that's pretty amazing. So if you have a server-grade computer, you will of course be able to do much more, and you will get an even lower latency. Okay, so how can you use this? How does it fit with your infrastructure? SpeedMac can use pretty much any normal database. It can use also files like CSV or bin files, and it just connects. You select the type and you can connect, and it will extract all your metadata. You can deploy anywhere. You can use Docker and Kubernetes. You can deploy on any cloud service or on premises. It integrates with the big three IDEs that are out there. And you can deploy them also on web services, any of them, basically. So that concludes my presentation. So by that, I open up for any questions you might have. Everything was crystal clear. That's fantastic. Never happened.
I just got a quick question.
Sure.
So I get the JVM stuff. Being naive, are there ways to do that in other environments? I mean, maybe like obviously C would probably somehow figure that out. But like, I'm just curious. Like, it obviously be much more convenient to have the JVM do it for you. You don't have to worry about managing all that stuff.
Yeah.
Are there other ways to do that kind of stuff?
Not that I'm aware of in Java, but if you use other languages, of course, like C, you can allocate your own memory. That's basically what we're doing here. It's like we're having our own memory manager, doing our own garbage collect, but on another level. So what we basically have done is to implement a new memory system that's not the Java system. And that can work directly with primitive objects rather than just normal Java objects.
You're basically recreating it yourself, which is a lot of work.
Yeah, it was a lot of work, yes, for sure. Yes?
How does it work when the data is generated in real time and being processed in real time, because there's some delay involved in
Yes.
writing the real time data?
That is true. So that's something we have to be clear about, that this isn't really suitable for a high transactional load. This is more of a data analytics fit. But having said that, you still can do a lot of updates. You can renew your snapshot maybe every minute or every 30 seconds, and you can feed in updates into the snapshot and can create a lightweight snapshot of your data. So you can kind of have new snapshot every second or every 100 milliseconds, whatever you want. And that's a comparatively cheap operation to update things in the snapshot that you have. So there are ways to do that, but I wouldn't recommend this technology for like if you have 1 million transactions per second, then this is not a good solution. But if you have thousands of operations per second or updates, that's okay. That can give you a picture where the space is, where the fit is.
High-speed streaming data and streaming transactions, so like look for something else.
No, yeah, if you have like I said, millions of updates per second, then you need to do it in another way. Because these snapshots, they are immutable, and because they are immutable, they are inherited thread saves. So that, and also they are much quicker because the CPU and everything can cache things much better, whereas if they are volatile, you need to have thread safety built in, and that will cost you a lot of performance. So we are geared towards read optimization. Okay. Thank you so much for showing up. Thank you.